Um, so what are atoms like? What do they look like? So now that we've gone through a bit of decay and what's going on, what do atoms actually look like? So we like to look at what we refer to as Bohr's model. Now, none of you should have seen this movie being in year 11, but I'm sure some of you might have gone with your parents. And you may have seen the movie Oppenheimer. The Bohr that they actually discuss that he meets when he is at university in Germany, when he goes to Germany when he's younger, is actually Neil Bohr. It's the same bloke. This is his theory. So it's kind of cool. For me, that movie was actually kind of cool in terms of seeing this. I was like, wow, these are people that, I've learned what they are discussing. Yes, they are just actors playing them, but at the same time, it's cool seeing that, real life history being played out. But essentially, in Bohr's model of an atom, there are fixed energy levels that electrons are found in, and these are known as electron shells. So electrons move from a lower energy to a high energy when they absorb energy. This is known as excited, and when excited electrons immediately return to their original or low energy levels known as ground state. So essentially what they do is they move up really quickly and they move back down really quickly. So they go up, oh, I'm excited, oh, I'm back. It's like an immediate up and down. In this process, they release that excess energy that they absorb. So they absorb energy and they move forward and they go, actually, I don't want this energy. They go back and they release it. That released energy comes out as light. And you can sort of read what light energy is coming out and say, all right, it was this color or it was this intensity, therefore I can say that I'm working with these levels of energy in these shells. It's actually something you can do. So as you can see here, you've got 3 shells here. You've got some energy that hits an electron. You've got a lower energy state. You've got a high energy state. The electron moves up into an excited state. It goes, oh, I'm really excited right now. I've got a lot of energy. I move forward. So it moves into this excited state. And then it goes back down. And when it goes back down, it re-releases the energy, but it transitions it into a sort of a light approach. So now it's like acting as a light. So this energy has gone up, and now it comes back down, and it goes, all right, I don't want this energy anymore. I'm getting rid of it. And it gets rid of it the best way it can, and it does that by emitting light. So, as you can see here, there are a whole bunch of shells that you need to know, and the number of electrons that are in them is determined by 2 times n squared. So, if I say I have 2 shells, I go 2 squared is 4, 2 times 4 is 8. If I go, all right, now I have 3, so I go 3 squared. 3 squared is 9. 9 times 2, 18. Now I have 4, so I go 4 squared, that's 16 times 2, I have 32. So the max number of electrons changes depending on the number of shells. However, you will only ever really work with 4 shells, and your 4th shell, you will only ever really work up to 2 more. So you only work up to about 20 electrons usually. You can go further. You will discuss it at sometimes in some occasions, but most of the time you're maximally going to go to 20 electrons. So you're going to go max in the shell is 2, max in the outer shell is 8, max in the outer shell is another 8, and then so forth. But we'll discuss this in a second. But as you can see here, this is sort of what we were discussing. This is Bohr's model. So his model can only explain the emission spectra of one element, hydrogen. And there are a lot of assumptions in this model, which he could not explain, but could sort of prove most of them to be true. So we switched to sort of Schrodinger's model. So Schrodinger's was the next model to come along. Schroeder essentially took Bohr's model and he improved it with quantum mechanics. So he kind of went to the next level. So electrons are now considered to have a wave-like property. So if those of you who have done physics, and this is the reason, this is a sort of a very technical part of chemistry that you don't need to know in super duper detail. But what you'll find is that in physics, you discuss this idea that light and particles act both in a wave, but also not in a wave. And it's kind of this hard idea to get your head around that they have properties of both, and you're like, I have no idea what's going on. Don't worry. Scientists who have studied their entire life still don't know what's going on. You don't need to figure it out. But electrons are thought to have a wave-like property as well as just a physical property. And so he suggested that the electrons were not in orbit, but rather they were in a cloud in regions of space, which we called orbits. Now these orbits, he still referred to as shells. So he said, all right, they're in a shell. This is the major energy within the atom. But they also have subshells. And these are energy levels within these shells. So you have an S, a P, a D, and an F. There's a lot more, but these are the first couple. And then you have orbitals. So orbitals are essentially the regions within these subshells where electrons are found. Now, you don't need to know about orbitals. Probably a bit too far. You're not going to discuss them all that much.